Okay, we're going to continue our discussion about thermochemistry, and so far what we've talked about are physical processes. In other words, calculating how much energy goes into and out of water and metal in the process that we called calorimetry. Well, now we're going to take a look at chemical reactions. So we'll look at how much energy is put into a chemical reaction to make it happen, or how much energy is released in a chemical reaction. First of all, you need to know that this is going to be a very basic explanation about energy involved with chemical reactions. We're going to do some math behind it. It goes into much more detail and in depth as you move on in chemistry. So this is a basic overview. So first of all, when we talk about energy with chemical reactions, we're going to use that term stoichiometry again. So we're going to write some chemical reactions, and then we're going to do the math that corresponds to those reactions. When we talk about energy in chemical reactions, we're going to refer to it as enthalpy, and it's going to have the symbol H. Now later in chemistry we'll talk about delta H, which, as you know, would be H final minus H initial, but we don't really need to worry about that right now. What you need to know is that when we talk about H, we're basically talking about the energy of chemical reactions the same way when we talked about Q involved with Q is equal to MC delta T in physical processes. So when we were talking about the physical process of water heating up and cooling down, we called the variable for energy Q. While for chemical reactions, we're going to refer to it as H. Now here it says Q is equal to H, and that's not technically correct, but for our purposes, it'll just be fine. So when I talk about the enthalpy of a reaction, what I'm talking about is the energy that is absorbed by a chemical reaction or the energy that is released by a chemical reaction. So refer back to this if you need a reminder about what H stands for and what the word enthalpy stands for. All right, when we look at chemical reactions then, the sign for H is going to be the same as it was when we used Q. So when we said Q was exothermic, we said the sign for Q was negative, and when Q was endothermic, we said the sign for Q was positive. It's the same thing with delta H, or enthalpy. When the reaction is exothermic, the sign for H will be negative, and when the reaction is endothermic, the sign for H is going to be positive. The way we indicate this in a chemical reaction is by writing the word heat as either a reactant or a product. So in an exothermic reaction, heat is being released, so we're going to treat it like a product. In other words, it's giving off heat, so we're going to write the word heat. So when you write this chemical reaction, you would write calcium reacts with water to form calcium hydroxide, releasing some heat. If a chemical reaction is endothermic, in other words, it absorbs energy, we're going to write the word heat as a reactant. So if this is an endothermic reaction, we would say sodium bicarbonate absorbs a certain amount of heat and releases sodium carbonate, water, and carbon dioxide. So if the chemical reaction is exothermic, indicated by a negative sign for H, we write the word heat as a product. If the chemical reaction is endothermic, as indicated by a positive sign for H, we write the word heat as a reactant. Okay, so let's do some problems now where we're actually doing something with this idea. So we have a chemical reaction, and as usual, we're going to balance that reaction first. So I'm going to put a 2 there. Oops, that's supposed to be a 3, and I'm going to put a 3 there. Now, you can see the way this chemical reaction is written. You've got a certain amount of energy, and remember, joules is the unit for energy, so we have kilojoules. that unit for energy is written as a product. So we would know that this reaction is exothermic, and our value for H, or the sign, would be negative. The value of it is 231. So if I said, what is H for this reaction, or what is the enthalpy of this reaction, we would say that its value is 231 kilojoules. So let's solve a problem using that idea. How much energy, so when we're done, we want units of joules, will be released when 13 grams of nitrogen reacts. So think back to when we talked about how to set up problems. I'm going to write 13 grams of nitrogen, and I'm going to solve for joules. Oh, I guess we could solve for kilojoules since our unit of energy is in kilojoules. Same idea. Alright, so let's start with the given. 13 grams of nitrogen. Now remember, nitrogen is diatomic, so we write it with a subscript of 2. And you know what I'm going to say next. We're going to draw our fraction. What goes in the denominator? Grams of nitrogen. Now in this case, what we're going to do is convert from grams to moles of nitrogen. And if you remember, 1 mole, 1 nitrogen is 14, but we've got 2 of them, so we have 28 grams of nitrogen per mole of nitrogen. Our grams cancel, and we have moles of nitrogen. Now here's the trick. You know we're going to put moles of nitrogen in the denominator, and the way this works with energy is we take our value for delta H, which is given, or let's just say H, and we're going to have 231 kilojoules of energy per how many moles of nitrogen there are in the reaction. So you get that value from the coefficient in the reaction. And remember, if there's no coefficient written, it's implied that it's a 1. So our moles of nitrogen will cancel, and then when we do the math, we should get 107 kilojoules, which will be our unit for energy. Now there's another way to do this, and I'll illustrate that in the next example of how you would do this dimensional analysis. So again, the next problem, it says how much energy, so again we're going to solve for kilojoules, will be released when 2.5 liters of hydrogen reacts. So this time we're going to start with 2.5 liters of hydrogen, and again it's a diatomic. So we're going to put liters of hydrogen in the denominator, and again we're going to go to moles of hydrogen. And if you remember from our dimensional analysis, there's 22.4 liters of hydrogen per mole of hydrogen. We're assuming that this all takes place at standard conditions. So our liters cancel. Well, now we're going to put moles of hydrogen in the denominator, because we have moles of hydrogen here. Now here's the new technique, and you don't have to do this, but you'll see this if you look around the internet a little bit. We can say that there is 3 moles of hydrogen. The coefficient in front of hydrogen in the balanced equation is 3, and then we would say per mole of reaction. RxN is the abbreviation for reaction. Then what we would do is our next conversion factor, we would put 1 mole of reaction in the denominator, and then our value for H in the numerator, 231 kilojoules. The idea behind this is that you treat the whole reaction as one thing. So we say 1 mole of this reaction produces that much energy, and the coefficient, we say there's 3 moles of hydrogen per this whole thing. So that's where you'll see this idea of mole of reaction. Again, what you could do is just, instead of writing mole of reaction there, you could write 231 kilojoules, as long as your number in front of the moles of hydrogen matches your number from the chemical equation. Either way will work out fine. So when you do that, you're going to get 8.6 kilojoules. Alright, let's take a look at another problem. And this vodcast is going to run a little bit long as I go through these problems, so you can fast forward where you need to. Okay, so now we have the reaction given, and it says delta H is equal to positive 23.5 kilojoules. Now we know that's going to be endothermic because our H value is positive, so if we were writing this in the reaction, we would actually write the 23.5 kilojoules as a reactant. But I'm not going to put that there because I want to keep this somewhat neat. So anyway, let's start with the given in this first one, and that's going to be 32.4 grams of carbon disulfide. So what we're trying to find is how much energy will be required. So we're going to do the same thing. Molar mass of carbon disulfide is 76 grams per mole of carbon disulfide. So our grams cancel. And then again, we're going to put moles of carbon disulfide in the denominator and our energy in the numerator, kilojoules. And we're going to put the coefficient in front of carbon disulfide from the formula, which is 1. So everything is going to cancel except kilojoules. And when we do the math, we'll get 10.02 kilojoules. Let's take a look at the next one. Again, we're solving for energy, and we're starting with 21.1 liters of sulfur dioxide. And again, we're going to assume this is at STP, so we can use our conversion, 22.4 liters. Let me rewrite that so that looks a little better. Excuse me. 22.4 liter. Now it looks like a 9 again. Again, sorry. There. Per mole sulfur dioxide. So let's cancel out the liters. We want moles of sulfur dioxide in the denominator. And again, we're going to put our energy in the numerator. We're going to find our number for sulfur dioxide from the balanced formula, and that value is 2. So our moles cancel. And again, when we do the math here, we'll get 11.07 kilojoules. Alright, let's take a look at one where we solve for a different unit. And in this case, what we're going to solve for is grams of sulfur dioxide, starting with 500 joules of energy. So right away I'm going to write that as 0.5 kilojoules, because I can convert from kilojoules to joules by moving the decimal 3 places. And what I'm going to do now is I need kilojoules in the denominator. So our energy, 23.5 kilojoules. Now remember, this is kilojoules per mole of whatever we're talking about, and we're trying to get sulfur dioxide. So I'm going to say 2 moles sulfur dioxide. That 2 is coming from the balanced equation, and this is our heat for that reaction. So our kilojoules cancel, and now we're going to convert from moles of sulfur dioxide to grams of sulfur dioxide. Molar mass of sulfur dioxide from the periodic table we said is, what is that, 64? 32 times, yes, times 2 is 64. So anyway, do the math. 0.5, this one I do need a calculator for, times 2 divided by 23.5 times 64 gives us 2.7 grams of sulfur dioxide. So what this shows is that you can do the dimensional analysis, and again, it's all starting with the given unit and canceling until you get the unit that you're looking for. So we'll do one more like that. Again, I'm going to write this as 0.350 kilojoules. So I'm going to put kilojoules in the denominator, and it's 23.5 kilojoules per mole. And again, we're looking for carbon now, so I'm going to go up to the balanced equation. The coefficient in front of carbon is 5, so our kilojoules cancel. 1 mole of carbon from the periodic table is 12 grams, so our moles cancel. And we're going to do the math. Times 5 divided by 23.5 times 12, and we're going to get 0.89 grams of carbon. So what you can see is that you're just doing what we've done before with chemical reactions and dimensional analysis, with this idea that if we know how to write energy in the chemical reaction, in other words, as a reactant or product, we're just doing the dimensional analysis to figure out what unit we're looking for, like we've done times before. So you're going to do some practice problems with this, and you can go through and watch this podcast over a couple of times. And this one did run a little long. So again, pick the problems that you need to do, review those, and we will go from there. Again, don't hesitate to email me questions, and I will see you in class.